The problem I decided to do was on a Grubhub delivery robot. So the idea of this problem is that the robot is going to start in Hit Hall and it's going to make its way to Ambler Johnston and then back. The reason I chose Ambler Johnston is because it has a lot of accessibility through Washington Street and West Campus Drive on one end, and then up through Drillfield Drive on the other end. So I thought it'd be an accessible hall to pick, and it's also not too terribly far away. You don't have to cross the campus diagonally. It's pretty much a straight vertical shot to hit hall. So the idea is that the student is going to have to solve for two main things. One, the energy consumption of an individual trip of the delivery robot from Hit Hall to Ambler Johnston and back, and then also for the battery degradation and how many trips the robot can take before it has to have its battery replaced. Okay, so the two graphics that I have here is one, the battery capacity on top of the cycle number. So the whole idea is that this red dashed line is sort of a like an arbitrarily set value for the number of cycles or for the amount of capacity the battery has left. And as the battery's used or as the battery like cycles from full to depleted, the capacity slowly gets lower until it crosses this threshold, in which place it would need to be replaced. Um, yeah. So the other graph I have here is just a little bit of a map of the like the type of path I would expect it to follow. Nothing crazy. Okay, so the first part of it is to of the problem is to figure out the energy required for one delivery. So it's uh I gave three equations to help this out. The first one to look at would be the power draw equation because um or I guess it would be the energy consumption equation because that is kind of what you're looking for, which I mean a basic physics idea is that energy is the integral of power with respect to the time that the power is being drawn. So I even though that kind of seems like a simple step, I included it specifically so the students would get practice using trap Z and just like integration approximation, which was a pretty key aspect of, or at least it was like it was a not necessarily a key aspect, but it was a pretty it was like a lesson that we went over and a thing that we were tested on. So I thought it would be good to help the students practice with that. Um, to get your P of T, first you go to the power draw equation, which is just torque times angular velocity. And then just for a little bit more math, we split up the angular velocity into the 2 pi times the rotations per second. So I mean it's not going to be necessarily difficult at all to calculate the angular velocity. It's just like it's genuinely just multiplication, but you know, it's something else to add. Yeah, so moving on down to the solution here, which is up here and then down here, the wh- you first calculate the angular velocity, like I said, very simple, only simple multiplication, and then same for getting the power or evaluating the power equation. So that I mean the main part of it would be the trap Z down here, the integration approximation, right? You would do the range of T, which capital T would be the full time it takes to do one loop of the like one loop of the delivery route, which would be given. So then that'll give you your range of times to use, and then P will be the power draw from the robot usage. So then you'd have NRPS would be a given value, tau for the torque would be a given value, and then through that you could evaluate all the way up to the power draw really easily, and then use your trap Z model to find the energy drawn, which is pretty simple. Okay, so then you move to part B and you get to the whole battery degradation thing. The I was looking through this like I think it was a master's thesis, so I wasn't 100% sure what was going on, but it had this equation, but it was a function of T for temperature, like the temperature that the battery was running, and N, and then it would be A, it's like A T N plus B zero times T. But if I figured like it doesn't have to be super complicated or realistic, and if you just keep the T constant, it would turn the A and the B of zero into a constant as well. So it's like no big deal there. Um, so then yeah, it gives you constants A and B zero here so that you could again you can like actually evaluate it. And then the second equation here would be the like this is kind of what is represented by the graph. So the E use would be the energy consumption that the student would have figured out in part A, and then the Q of N would is just like the number that it's the cycle count basically. So then Q of N max would be like the final cycle, or I guess the number of cycles before um you'd have to replace the battery. So yeah, you can go down into the script here. Um, I mean, nothing particular. Oh, and then oh yeah, okay. The whole solution is here. Nothing particularly crazy here, but it's sort of just like more of the some of the other principles the from like this the between chapter one and chapter two of the class. And then for the analytical question here, um I was just like wanting to make sure that the students really understood what was being asked and what was being represented in the battery degradation equation. So it's kind of just like asking about that, and it's asking to like while it was the whole battery degradation equation is linear here, it's that's not really a realistic thing that would happen in the real world. So there's it's asking the students to touch about that a little bit too, just because like it's important for them to not get that misconception in their head and to understand it's more complicated than it's being presented in this equation. So then yeah, it talks a little bit about like how B0 is the initial capacity, and then A is the rate at which the capacity is lost, and then the N would be the number of cycles, which acts as the variable in that equation. So then and then this is what I was talking about earlier with how the linear model is simple and it's there for the purpose of the equation, but it's not realistically what would happen. And then here are my sources for the different equations that I drew up. So sources three and two are cited here, and then source one, um, it's supposed to be right here. Let me amend that real quick. But yeah, I think that's all. Thank you.